Hi, welcome back to Math 533, Topics in Euclidean Geometry. This is our last video for week 12, and in this video, what we're going to talk about are the altitudes of a triangle. And so here's an altitude. The altitudes of our triangle and what's called the orthocenter of the triangle. Let's start with a definition. The altitude through a vertex A is the line segment perpendicular to the opposite side, so in this case BC, that's incident to A. Now sometimes in the literature people are talking about the line. We're going to talk about line segment unless it's clear from the context we really mean the line, right? And as you know from any one of our axiomatic systems, a line segment can always be extended to a line. Okay, the point of intersection between this altitude and the side, or I should say the line BC, is called the foot of the altitude. And the length of the altitude is called the height. You may remember this from, for instance, the area formula for a triangle, which is 1/2 base times height. But the height here is referring to the length of one of the altitudes. Okay, and we have an unusual verb here for constructing the altitude through the point A. We call it dropping the altitude either at or from A. And I guess this picture is kind of silly because my altitude doesn't look like it's going up and down, but the picture that people have in mind is you have a vertex and you have the altitude sort of falling from it. So the theorem that we're going to prove or I guess sketch in this video, and then have you flesh out the details in the homework, is that altitudes are concurrent. So they're concurrent in a point. For some reason, we often write it as capital H. I guess that's H for height. The point at which they're concurrent, is called the orthocenter of the triangle. Okay, and the idea of the proof is to piggyback off of the homework that you did this past week, in the week 11 homework, where what we do is we construct a big triangle, and I'm going to call it A prime, B prime, C prime, and we want the big triangle to have ABC as its medial triangle. So this A prime, B prime, C prime is sometimes called the antimedial triangle. And then the key thing you do is you say, okay, the altitudes of the triangle ABC, at least if you extend them into lines, are precisely the perpendicular bisectors of the triangle A prime, B prime, C prime. And then you proved already that the perpendicular bisectors are concurrent. And so then in the homework, I want you to flesh out this line of reasoning. So let me show you what this antimedial triangle looks like. And so here's my triangle ABC. And if you look at it, I've constructed now this big triangle A prime, B prime, C prime. And if I've given you the hint that, well, I guess the first hint we have is that C needs to be the midpoint of A prime, B prime. Right, if this altitude here is the perpendicular bisector of A prime, B prime, that much is clear. Or honestly, right, ABC is the medial triangle of the big guy, so C has to be the midpoint of A prime, B prime. We know that the big guy is similar to the little guy. So just using that, you should be able to figure out what A prime, B prime, C prime need to be. So do take a look at the homework and see if you can flesh that out. Okay, that's it for this video. Before you take a look at the homework, I do encourage you to think for a little bit about how you would construct the anti-medial triangle. I've explained a little bit more of how you construct it in the homework question, so that you're not completely stranded if you can't figure out how to come up with it. But do think about it for a little bit, because I think it's a fun construction, and it's a good chance to exercise your geometry thinking muscles. Okay, thank you for watching. I hope you enjoyed it. That's it for week 12, so we'll see you next week when we start talking about the Pythagorean theorem. In the meantime, happy mathing.